go through kind of how we're going to manipulate the data. With this, there's really not much that we need to do besides just doing some basic calculations. And so just remember that, momentum, which represented with P, is going to equal mass times velocity. So really that's the main type of equation that we're going to use. Now, I'm going to zoom in a little bit here just so it's a little bit easier for us to see. The first thing we need to do is just fill in our masses. And what I want to do is I just want to show us ways that we can do this without having to do the calculations, but use this tool as a resource. So when we have to do calculations, we need to tell any spreadsheet to do equals. And then we're going to find the total mass, we simply need to do the mass of the empty cart plus the added mass. And I get 0.781. Now, if I want to just repeat this process, I can just simply drag down here. But you'll see that that actually doesn't get me what I need to, right? And so when it does that, it's going to drag down B1 to B2, and it's going to drag B4 to B5. So what we want is we actually always want these values added to this value. So instead of having to type it in each time, what we can do is we can go back and put a $sign in front of the B and in front of the 1. Basically what that means is we always want this to be B1 added to whatever else it's going to be. So this autofills, which is nice, but what I could do is I could just click on this, grab this little thing here and drag it down. And so then I get B1 plus B5, B1 plus B6, B1 plus B7. We're going to do the same thing over here for cart 2, where I'm going to equal B1 plus E4. It's going to autofill for me, and I'll allow it to do that. Again, another way you can do it, just click on the cell, move my cursor so I get that little crosshair, and then drag that down. So that's my total masses. And one thing what we're going to do is we're going to make sure that our velocities actually make sense. Okay, so in this case, this is my stick together. And so what happens is whatever my initial velocity is, when the cars stick together, they're going to continue moving in that same direction. So it really doesn't make sense for these two carts to actually have different direction of velocity after the collision. So what I'm going to do is I'm going to take these values and I'm going to replace them with a positive. Basically what is happening is when we took the data, one cart was facing one way, one cart was facing the other way. So that's why one's positive, one's negative. But we're just going to imagine them as all being positive in this case. Now, when they bounce apart, there definitely are cases where velocity 1 after the collision could be a negative. But in this case, positive actually makes the most sense. Okay, so now we get down here to cart 1, and we're trying to find the momentum before the collision. So that's going to equal the total mass of cart 1 times the velocity before the collision. So I'm going to fill that in. It's going to allow me to autofill that, which is good. Which if I double click, I can see, and it highlights the cells, right? I want the total mass times the velocity for that trial. We can do the same thing for cart 2. That's going to equal the total mass of cart 2 times the velocity before the collision. It's going to autofill that. Really, these are close enough to 0 that we could probably just simplify those to 0. But for this group, because they did have some data there, we'll just allow that to stay there. After the collision then, it's going to be the same process. I'm going to find the total mass times the velocity after the collision. Fill that in. And then same thing for cart 2. Mass times velocity after the collision. Allow that to autofill. Then what I'm going to do is just look at the total. So all the total is simply going to be just the momentum of cart 1 plus the momentum of cart 2. We'll autofill that. and then also the total momentum after. So total momentum of cart 1 plus the momentum of cart 2. We'll fill that in, and we'll see. So now if I just simply take a look at these numbers, okay, you know, this is about 13, this is about 12. It's really close. We get, again, about 12, 19, not really as close in that circumstance. But we do have here, you know, 0.24 and 0.23, 0.34 and 0.37. So what I want to do is I'm going to actually calculate a percent difference. And we're going to do that because these two should be the same. The total momentums based on the conservation of momentum before a collision and after a collision should be the same. And so we're going to calculate a percent difference based on the differences. And what that's going to be is that's going to be the difference between the two values on top. So we'll have this value minus this value. And that's going to be divided by the average of the two values. So we're going to have this value plus this value divided by 2. So you can see if my parentheses are good. If there's a red parentheses, it basically means there's no matching one. So I'm going to get rid of that. And then I'm going to turn that into a percent of 10%, which again in physics is actually a pretty good result for the data that we collected. And now not all of them are going to be good. We could predict this one just based on the natural differences that's not really good. But all the other ones, 6%, 10%, that's really good in terms of the values that I collected. And so what we're going to use this for is this is just helpful practice of how I can manipulate data in a spreadsheet and how I can see, does this data support the concept of momentum being conserved? So obviously 3 out of our 4 trials are really good. And we can talk about, you know, how could we eliminate maybe this result here, and what are some maybe lab practices that we could do to help limit this percent difference of 50% from what it should be.